All right, this is the second lesson that I'm going to do on relativity, and I'm just going to be honest with you. I don't feel like I have the best grasp in the world on relativity. It is relatively simple to grasp the concepts, but actually believing them, and especially if you move past special relativity into what's called general relativity, it becomes extremely complicated. But basically what we said last time was that Einstein accepted the results of the Michelson-Morley experiment, which said that light always travels at the same speed. It does not matter what the motion of its source or its detector is. So that if I have two spaceships coming at each other and one shines a light at the other one, even if they're coming at each other at the speed of light, the light that's heading toward them will hit at the speed of light. In fact, more than that, if I have two spaceships that are coming at each other at the speed of light, they are heading toward each other at the speed of light, not twice the speed of light. You can't go faster than that. And the result of that is that we have to rethink what we think about things that we have always assumed were the same. I'm going to do this over here so I'm not off the screen. But basically, speed, which is velocity, is distance divided by time. Now, for low speeds, this equation works. But if we're talking about the speed of light, c being the speed of light, is distance divided by time. Since this is a constant, the only way that can be constant is if either distance is changing or time is changing. By the way, if c was saying the same, they both could change, but at least one of them has to change. And so last time we ended with an equation, which at first seems a little bit odd. I'm going to actually have something for you to read, and you can look at this closer. But we come up with what is known as the time dilation equation. And the time dilation equation says that if you had a person in a frame of reference just means where he is, and he considers himself to be the center of the universe, so to speak, and another object goes past him at a particular speed, that the clock, the time, would be slower for that other object. Now, when I say it's slower, I don't mean some sort of trick, like the clock is just running a little slower. Time is actually slowing down for that particular person. What's odd is that because the frame of reference doesn't matter, if we have two ships coming toward each other or passing each other, and this one looks at this one, this spaceship A, will see spaceship B clock actually running slower. Time is slower for him. And the same thing would be true for this one. His time seems normal, and this one's time is slowing. And you say, well, how can both be true? And yet that's what you have to accept with relativity. This equation, I didn't have time to, we kind of went long last time, but if you look at this equation, what's going to happen is that if this velocity gets close to the speed of light, this on the bottom is always going to be less than 1, because if this was exactly 0, then this would be the square root of 1, which would be 1, it would be the same. But as soon as v gets a little bit large, we're going to start to notice a difference. So I made up a little table. And what I did was I put the velocity as a percentage of c. So this would be 0.1 c, 0.25 c. By the way, that's really fast, right? That's really, really, really fast. And let me go one more, 0.99 c. So 0.5 c is 1 times 10 to the 5, 1.5 times 10 to the 8 meters per second. This would be 3 times 10 to the 7 meters per second, so that would be 30 million meters per second. This is faster than anything that we can conceive of. And what I have done is worked this equation out for it. I simply put that in, like say take the first one, I went t0 over the square root of 1 minus 0.1 squared, 0.1 c squared over c squared. The c squareds will cancel. And what you come up with is a ratio. So what I did is I put time here as 1 hour. So if the two aren't moving relative to each other, I should have done it this way. If the velocity is 0, c, then t0, t here will be equal to this would be t0 would be the same as t. But here, 0.1, this is going to be 1.005 t, which would be 60 minutes and 18 seconds. Okay, not very much, 60 minutes and 18 seconds. But what we're saying, and we're really serious, is the person in the spaceship, his time would have slowed down. So it takes him 60 minutes and 18 seconds on his clock when the other clock is going at exactly 60 minutes. So I did it as 1 hour is what I did. And if we go up, let me just put them on here. This is 1.03, 1.15, 1.51, 1.6, 2.29, and 3.2, and 7.09. Which means that this would be about 62 minutes, and about 69 minutes, and about 100 minutes, actually 91 minutes here, 100 minutes. This would be 2 hours, 18 minutes, 3 hours, 12 minutes, 7 hours, and about 5 minutes or so. Now, you may ask the question, has that ever been tested? And the answer is yes, it has. They did this. They actually took an atomic clock, left it on Earth, put it up in space in an orbiting satellite, which isn't anywhere near this, but went long enough so that they could predict what the time was, and it was perfectly predicted, right? By the way, the theory of relativity, they believe, is the most tested theory in the history of science. They've thought of all sorts of experiments to try and prove the theory of relativity. Now, there are two other things that happen. This is called time dilation, but there's also length contraction. Remember, both time and distance could be changing. If time is getting slower, this getting bigger, if that got smaller, those two would adjust and keep v exactly the same. And that's exactly what happens. So this is L is equal to L0 times the square root of 1 minus v squared over c squared. What that does is the exact opposite of this. What this means is that if you had something that was going at 1/10 the speed of light, then the length would be 1 over 1.005, or that length would be a little bit shorter. In other words, if we took a measuring tape in the first spaceship and measured the same length in the second spaceship, it would be shorter. Space has actually contracted. The universe is not flat. Einstein understood the universe to be a curved space. And the space curvature was based on the distance between things depended on how fast you were going. So this is called length contraction. And then one other interesting one is mass dilation. And mass dilation is the exact same equation. those are your three equations. So the same thing, if we were to take and check the mass of something that was traveling, say, at 75% the speed of light, if it weighed a mass of 1 kilogram, to the person in spaceship 1, in spaceship 2, it would have a mass of 1.5. Now, there's a famous paradox, which is called the twin paradox. It's not called a paradox because for the reason that you think, but I don't want to go into it right now. But what happens is, let's say that we were to take and have twins that were born, and those twins were born obviously on the same day, and when they were born, this is terrible, but we're going to put one of the twins in a spaceship, the other twin's going to stay on Earth, and this spaceship is going to go off at 95% the speed of light. And when it goes off 95% the speed of light, and then it turns around and it comes back, and it takes it and it lands, and that takes 21 Earth years. So that this twin has just reached her 21st birthday. The twin that was in the spaceship, because it's traveling at 95, would basically be the time on Earth was going 3 times faster, 3 times slower, and this twin would come out and be 7 years old. Not a pretend difference, but an actual difference. I said I wasn't going to say why it's a twin paradox. It's a twin paradox because I've said it doesn't matter which one is moving, but it turns out this one had to accelerate and decelerate, and so the effect will be here. That's the second general theory of relativity, and we're not going to go into that. But it's a really, really odd thing. Now, one of the things that Einstein had to do was that he had to ask the question, how is some of this possible? And some of you may remember, well, I don't know if I want to say it that way. What he understood was that space actually had curvature to it, that gravity warped space, that light or anything traveling at a particular speed would follow the curvature of space. He actually explained gravity that way. But these equations explain to us what happened. Now, this one we haven't really talked about yet. Why does mass dilate? And that was Einstein's great insight. We'll talk about that on the next one. This is where the equation E equals mc squared comes from, which is the key idea in a sense of relativity. So I should say the key idea, but one of the key things that people know about it. This idea of the time dilation, I have a little video I want you to watch that will blow you away, and there will be a discussion on it, as you can imagine. But it is, and then I have another video that talks about what curvature of space looks like. I wish we could be at school. Some of you may remember I have a big trampoline that I put up. It's actually a big a circle that I make out of PVC pipe, and I put on top of it bathing suit fabric, and we put weights on there. Some of you have seen those, seen it when I have that, and that actually mimics gravity. And there's a little video that will talk about that as well. One thing that you have to do when it comes to relativity is believe that it's actually true. If you don't, if you just say, oh, these are just scientists making stuff up, you're going to sell yourself short. Like I said, we live in a world of physics all year long where we're like the Pythagorean theorem. We can do right triangles. But the world is much more complicated than that. And you don't understand the universe unless you understand at least the ideas behind relativity. Let me give one example and then we'll quit the video. The orbit of Venus, not Venus, Mercury, was never able to be predicted under Newtonian physics. Remember how we talked to universal law of gravitation? We have force, we have the two masses, which we knew, and what the radius is. We should be able to figure out what the orbital velocity is, and the numbers never worked out. It was always off, and we couldn't understand why. Well, it turns out that you can explain it perfectly with Einsteinian physics, with relativity. We usually talk about non-relativistic or relativistic physics. You can explain it perfectly with relativistic physics, because what's happening is the sun is spinning, and that sun spinning is actually dragging Venus around with it and actually changing the orbit of Venus, because space is warping and Venus is getting caught up in that warp. It's doing that to us too, but we're so far away from the sun that it's almost indecipherable. And so when we say that relativity actually explains the universe better, that's not a joke. So that's not just somebody talking or me just talking, but it is where you have to sort of suspend the idea that time is the same everywhere in the universe and that lengths and masses are constant and don't change. That is not the case at all.